an important point is that you need, if you work with climate model, if you work with climate change projections, especially if you look at impact of climate change projection, is that you need to be aware that there are a lot of uncertainties everywhere. As an example, you have here from the literature projection of climate change in Africa for agriculture that are given by different papers that have been published previously and that use climate models to look at what could be the impact for millets, what could be the impact for groundnuts. Then you have the different projections by 2050, by 2030, by 2055, 2020. And you can see that there are large uncertainty with decrease of crop yield in a publication, a large increase in another publication. So you have a strong uncertainty. And all these publications use methods that are quite good, that are not that do not contain any error, but the fact that you have strong uncertainty. If you use one model or if you use another model, if you use one climate models rather than another, you have a lot of uncertainty between different models. So I will show you what is exactly this uncertainty. In fact, you have limitations in simulating climate of the future. First, you have emission scenarios that are the how we are going to increase our emissions, if we are going to be able to reduce drastically the emission, rapidly the emission, the CO2 emissions, and you're going to have a completely different climate in the future. So it's the first reason of uncertainty, the fact that we don't know what we are going to be able to do in terms of effort of reducing greenhouse gases emission. So the climate of the future is basically determined, is conditioned by our efforts in reducing emission scenarios. So we don't know how we're going to do in the future. Then you have also the climate models themselves that are not perfect. So there are a lot of processes we don't know about the climate. There are a lot of assumptions. You have a lot of hypotheses in the models. You have also computations uncertainties, which means that the model themselves and their intrinsic capacities to represent the processes that govern the climate are not well simulated, and you have different climate models and the representation are completely different. If you use one model, if you use another climate model, you could have completely different climate, even with the same emission scenarios. So that's why we use a lot of climate scenarios. We use average of different climate models, but not only one climate model. So to illustrate this point, you have uncertainty in rainfall projections for high-end climate emission scenarios. So the RCP 8.5, it's the scenario where you have the maximum of CO2 emissions, so the most pessimistic scenario. And you have the difference in terms of rainfall, the future changes in rainfall in the future for two different climate models with exactly the same emission scenarios, exactly the same simulation, but these are two different climate models. It's the model from CNRM in France and the model from IPSL. It's also in France, but in Paris. And you can see the difference in terms of rainfall, where you have the areas in blue, where we expect an increase of rainfall in the future, and the areas in yellow, where we expect a decrease of rainfall in the future. And if you look at West Africa, you have in one model a rainfall increase so an increase of the summer monsoon in this model, and in the other model, you have a decrease of the summer monsoon. So where you are interested in how climate is going to evolve in West Africa, in the Sahel, in Nigeria, in the Sahel, in Benin, in Senegal, you are interested in how the monsoon is going to evolve. And you can see that from one model to another, you could have an opposite signal from one model to another, which means that it's very difficult to anticipate what is going to happen for agriculture, what's going to happen for health, for water resources, because you don't know how the monsoon is going to evolve in the future. And you have also some problems with the models in representing even the climate of today. So to illustrate this point, you have two maps. The maps of observation of rainfall, so it's mean rainfall for climatological years. In summer, so it's the summer monsoon in Africa. On the left, it's the observation, and on the right, you have the result from one model, also for the same historical period, so the same years in a model. And you have the areas in green, in dark green, where there are the maximum of rainfall, and you have also in red the S08 400 millimeters per year, which is the limit for growing sorghum and millet. And you can see that in the observation, you have rainfall far north than what you have in the model. In the model, for instance, you don't have any rainfall in Senegal. You don't have a lot of rainfall in Burkina Faso. You have not so much rainfall in the north of Nigeria. So it's completely different than what you have in the observation. So the models have also problems in simulating rainfall of today. And so here it's the same graph with the observation on the top left, and the different maps are the result from the different climate models that from the IPCC exercise. And you can see that there is no truth there is no model which is the best. All models have errors. You have some models with too much rainfall, some other models with maximum that are not located in the good place. You have models with too dry models. So there are a variety of models, and you need to deal with such uncertainty with some good models, some other that are not very good. So it's something that you need to know, that when you're going to use climate models, they are not perfect. There are a lot of errors in representing the basic state of the climate. Here it's the monsoon, but you have also errors in representing uncertainty, in representing the future. So the good way to deal with this uncertainty is to use a lot of climate models, to make some average of different models, to use different scenarios, and not to use only one model and one scenario. Here it's a way to represent the uncertainty, where this uncertainty comes from. And in fact, you have different kind of source of uncertainty, which can vary over time. So if you are interested in projection in the next 10 or 20 years, the uncertainty is not the same that if you are if you are interested in the projection of the end of the century. You have here a numerical representation of the uncertainty. So the whole uncertainty is represented. You have by 1. So 1 is the whole uncertainty, and you have an evolution of the uncertainty that could come from a climate model. Sorry, I told you that climate model could be very different from one to another, but you have also uncertainty in scenario, so uncertainty emission scenarios. If we are going to increase strongly increase emissions, or if we are going to reduce drastically the greenhouse gases emissions, and you have also uncertainty in internal variability of climate. You know that there are ENSO events. You have a lot of variation in the climate from one year to another. So it's the internal variability of climate. And what you can see is that on the left of the graph, if you are interested in the next decades, the most important part of the uncertainty is the orange part. It means that it's the internal variability of climate. So we cannot make scenarios for the next 10 or 20 years without considering the internal variability of climate. If we're going to have an increase of frequency, of intensity of El Nino event, if we are going to have North Atlantic oscillation variations, they have a lot of internal variability which drives the uncertainty in the next 10 years. Then after, if you are interested in the 2040s projection, 2050, you can see that the area in blue is dominant. It means that there are a lot of uncertainty from one model to another. So you need, if you are interested in the 2050s, you need to have a lot of different climate models because they are strongly different from one to another. And then after, in the end of the century, you can see that it's the area in green which is dominant, which means that by the end of the century, the most important component of variability is the scenario. So if we are going to decrease strongly greenhouse gases emissions, we are going to keep on increasing greenhouse gases emission like business as usual. You can see that there are a lot of differences, and it will be the most important fraction of uncertainty. So it means that you need to consider these three kinds of uncertainties by sampling different models, trying to have different time frame, like midterm, like like fire end scenarios. You need to have different emission scenarios so that you can sample this uncertainty. Then after, if you are interested to simulate impact scenarios, you need also to know that these climate models are very coarse resolution. Typically, a mesh is something like 100 kilometers square. So it's very large, and you need to have information at local scale, at regional scale. And to do that, you need to perform downscaling using a high resolution model. You're using statistical methods. And from that, you can have high resolution data. You can have data without biases, and you can use then this local scale data for impact studies like hydrology, like agronomy, like biology, and so on. And this also contains uncertainty, which scaling method you're going to use. And you can also then force an impact model, like an hydrological model, like a crop model, to see how could change the water resources, how could change the crop yield in the future. So you have a whole chain of models, from the climate models to the downscaling models, and then to the hydrological model, just to simulate how water resources are going to evolve in the future.